Hello, Alvin ISD geometry students. Today we're going to be talking about geometric probability. So geometric probability is a probability that involves some kind of geometric measure. That could be something like length, angle measure, or area. So the first example we'll take a look at is length probability. You have your example listed here, so we're going to go and look at 1A. So we have segment JM, which they gave us our individual parts, but we want the probability that X, which is a point chosen at random, falls on the segment LM. And when we set up our probability ratio, your numerator is always the likelihood that your event actually happens. So LM's distance is 4. And we want to put that over the distance of the entire segment, which is going to be 14. We can express probability as a fraction, a decimal, or a percent. So this simplifies to 2 over 7, which as a decimal would be approximately 0.29, so 29%. Our second example, so finding the probability that X falls on segment KM. So KM's distance is 11, and again that's over the entire distance, which is 14, which expressed as a decimal rounds to approximately 79 hundredths, which would be 79%. Our next probability is involving volume. So iced tea at a cafeteria-style restaurant is made in an 8-gallon container. Once the level gets below 2 gallons, the flavor of the tea becomes weak. We want the probability that when someone tries to pour a glass of tea from the container, it is below the 2-gallon mark. So right here. So the probability that that would happen would be 2 out of the whole thing, which is 8. Well, 2/8 simplifies to 1/4, which we know is 25%. Then we want the probability that the amount of tea in the container is only between 2 and 3, so only right here. Well, that is only 1 gallon out of the whole, which is the 8 gallons. And 1/8 made into a decimal is 0.125, which would be 12.5%. We've looked at length and then we looked at volume, so now we're going to take a look at area. So if you look at the first example, we want a point E and it's chosen at random. And we want the probability that point E would actually be in the circle. So the probability that that would happen would be the the area of circle B over the area of the entire rectangle for circle A. So now we're going to go down to our example, and we have a skydiver landing on a target of 3 concentric circles. Remember, concentric circles are circles that share the same center point. So it says if the diameter of the center circle is 2 yards, so I'm actually going to come over to the side and draw it bigger so that we're able to see it. And you're unable to see color, so this outer one is blue, the middle one is white, and then the center one is red. So it says the diameter of the center circle is 2, and then it says the circles are spaced 1 yard apart, so this distance would be 1, and then this distance would also be 1. So for our first example, for 3A, we want the probability that the skydiver will land in the blue region. So only this outer part of the circle. Well, to find that, I'll actually have to take the area of the blue circle, which is the entire one, and then subtract out the area of the other 2 circles, which is actually going to be the area of the white circle. And then we'll put that all over the area of the total circle, which is, in this case, blue. So for area of the blue circle, if the diameter of the center is 2, that means the radius would be 1, which gives the blue circle a radius of 3. So area of a circle is pi r squared, so that would be 3 squared pi. And then I would take out the area of the white circle. So this white circle right here has a radius of 2, so it would be taking away 2 squared pi all over the total, which we know right here, again, is that blue, so 3 squared pi. 3 squared pi becomes 9 pi, taking away 4 pi, all over 9 pi again. Well, up at the top, these are like terms, essentially. So 9 pi minus 4 pi gives us a value of 5 pi divided by 9 pi. Since anything divided by itself is 1, we can simplify the pi's, which leaves us a probability of 5/9, which is approximately 56%. So I'm going to make a little space. So now we'll look at the second example. So we want the probability that the skydiver lands only in the white region. So only in this region right here. So now for our desired outcome, that's actually going to be the area of the white, but I need to subtract out the area of the red over the area of the whole, which is our total area, which we actually know is 9 pi. So I'm going to go ahead and substitute that in. Our area of the white we found over here was 4 pi. And then I'm going to take away the area of the white circle, which has a radius of 1. So if we're using the formula pi r squared, 1 squared is still 1. So I'm only going to take away pi. And again, that's all over 9 pi. So 4 pi minus pi, we get 3 pi over 9 pi. And again, our pi's simplify to 1, which leaves us 3/9, which is 1/3, or approximately 33%. Now on to our last example. We want to use angle measures to find geometric probability. So again, if you look at the splinter, you can't really tell the color, so we'll label this. That one is purple, blue, red, green, and yellow. So for 4A, we want the probability that the pointer lands on blue. Well, that angle measure is 70 degrees, so that's our desired outcome, over all possible outcomes, which in this case it's a circle, which sums to 360 degrees. We can divide out by 10, which gives us 7 over 36, which simplifies to approximately 19% chance of probability. So for example, 4B, it says the probability that the pointer will not land on green. This is important. So we're okay with it landing on anything besides green. So if 90 degrees is green, that means the sum of the rest of these would be 360 minus 90, which gives us 270, over the total, which again is 360. We can divide out by 10, which gives us 27 over 36, which we can simplify down to 3/4. And 3/4 expressed as a percent is 75.